Hello, here is a promised reasonable example of a linear Diophantine equation. Let's have something like 12x plus 45y equals, say, 6. So the first step in solving is to assess solvability. It might not be possible to solve it at all, and the criterion, the necessary and sufficient condition, is that the greatest common divisor of 12 and 45, whatever it is, should divide 6 neatly. So let's first compute the greatest common divisor using Euclid's division algorithm. The first step in this algorithm would be to take the larger of the pair and reduce it using Euclid's division. 45 divided by 12, how many copies of 12 can we fit in? Well, 3 definitely, 4 too many. 4 copies will be 48, will be larger than 45. So 3 copies fit comfortably, and the remainder is the difference of 45 and 36, and that is 9. So we can do the first step in the Euclid's algorithm, replace 45 by its remainder, which is 9. Then change the rows. 12 now divided by 9 gives us remainder 3. That's what we replaced 12 by. And after that we quickly converge down to the answer, because 9 is divisible by 3 without any remainder. So doing honestly this step of the algorithm, we end up with the stopping point. We end up with a pair something in 0. 3 is our greatest common divisor, and it does divide the right hand side, so we are in business. We can solve it, this equation, and find infinitely many solutions. So first step in doing that is to find a solution, just one pair of x and y, which will make this equation work. And first step in doing that is to find two numbers which will represent the GCD. So not to solve the original equation, but to solve an equation 12 some number, 45 copies of some other number together equals 3, equals the GCD. So that will be not solving our original equation, but because 6 is twice 3, we can take a solution to this and double it and get a particular pair, x and y. So let's again run the Euclid's algorithm backwards and find such presentation. So we start with the first meaningful pair, 12 and 9, and find presentation of the greatest common divisor as a combination of them. And that is just reading this division statement properly. So we can write 3 as 12, 1 copy, and then 9, 1 copy, but put on the other side is 9 negative 1 copy. So that is a presentation of the greatest common divisor as a combination of these two numbers, but we want to have a combination of these two numbers. We want to solve this Diophantine equation. And we can do it by taking 9 and rewriting it as a combination of 45 and 12, and then plugging it in instead of 9 here, because it is still the same 9, and then collecting the terms. So let me first do this substitution. I have this band equation sign to bring me down to the line of my true numbers, which I'm writing my GCD as a combination of. And so I have 12 one copy from here, and then 9 is replaced by 45 once and 12 3 times, and it is to be taken negative 1 time. So when I collect the terms, 12 appears once, and then 12 appears negative 3 times negative 1, so 4 times in total. And 45 is just negative 1 time. So if I write plus, 45 is negative 1 time. So now I have my u and v, or at least one pair. U I can choose to be 4, and v to be negative 1, and then I have a solution of this equation. But again, it's not my original equation, it's a simplified version of it. The right hand side is simplified down to the greatest common divisor. So to have a solution of my original equation, I have to take this equation and double it, both sides. So then on the right I will have 6, and then the 2 which I'm multiplying the left hand side has to be absorbed into u and v, changing them into x and y. So x will be twice 4 will be 8, and the y will be twice negative 1 will be negative 2. So again, you could check all your calculations at any step by verifying. So this pair 8 and negative 2 should solve our equation. Indeed, if we put 8 in here, we'll have 48, so negative, sorry, not 48, I said it wrong. So if we put 8 in here, we'll have 80 plus 16, so 96, and then twice 45 will give us 90, so negative 90 will be added to 96. What is left is just 6 as we want. So this is a correct solution. We have one solution. Then the statement done in the previous video allows us to produce infinitely many solutions, and moreover it will be the complete list of solutions. The procedure for obtaining all other solutions is slightly separate for each of the coordinates. So solution number k, if this is our zero solution, will be related to the zeros by k iterate of negative shifts when we take coefficient b, which is this 45, and divide it out by the GCD of a and b. And with numbers plugged in, x naught is 8, k is still a parameter, b is again is 45, and the GCD is 3. So all in all we have 8 without this is 15 copies of k. At the same time, y has to be manufactured from the zeroth solution by adding k copies, the same k, of a over the GCD. So in our case it will be negative 2 plus k copies of 12 over 3. And that simplified is just 4k minus 2, right? So that is it. That is the arithmetic form of solving our equation. So we have an infinitude. K is an arbitrary integer. We can take anything you like, negative 100 or positive 104. It doesn't matter. And then it's always good to imagine what happens geometrically with your solutions. They sit on the line. After all, this is a line equation, and they are also integer points on the plane. So let's see how, at least around the origin, how they look. The original solution is with coordinates 8 and negative 2, so I have to be really cramming down my units. So they will be negative 2 on the y coordinate in here, and then 2, 4, 6, 8. And this is the location of the original solution x naught, y naught. And then let's shift k from 0 to 1 and see where the point will appear. So the x-coordinate of that point will be 8 without 15. It will be negative 7. So now I'll have to go to the other side. Here's 2, 4, 6, and here's 7. And then the y-coordinate will be 4 without 2. So that is it. Will be 2, also 2, but with positive sign. So here is my position. And then the line should pass through these 2 points, and that determines the line completely. So I'll try to be careful drawing it straight. And then, well, that's basically it. We can see that getting from one integer point to another takes 4 steps up and then 15 steps to the left. And so the previous point with label -1 will be sitting somewhere here, and the next point will be sitting somewhere here. And they will be, of course, equally spaced, and of course there will be infinitely many of them on our line. Well, that's the generic behavior for integer points on the line. Where there are integer points, it will always be an infinitude of them there. So that's it for this video. See you later.